And we're back in lesson 18-3, learning today something called the triangle proportionality theorem. So we've been looking at triangles that are similar. We've been using this term proportional over and over again. And so we're actually going to learn something today called the triangle proportionality theorem that is hopefully going to make our lives just a little bit easier. So before we go too far, let's take a look at our learning targets for lesson 18-3. Our first skill that we're going to use today is we are going to prove the triangle proportionality theorem and its converse. Remember, converse is when we switch the hypothesis and conclusion of a conditional statement. For example, if A, then B, that's a conditional statement. And when we do the converse, we will switch the hypothesis, which in this case would be A, and the conclusion B. So it would be if B, then A. And I want to stress here that most of the time, when we in fact start looking at the converse, we see that it is just as true as the original conditional statement. So it helps our understanding when we apply that converse, depending on which kind of problem we're given. So once we prove the proportionality theorem, we're going to apply the proportionality theorem. We're going to use it and its converse. And again, I'll stress, oftentimes we use a converse depending on the information given. So we are continuing with this idea of Clarissa being a land surveyor, trying to find certain distances across certain parts of a national park. I believe in the last lesson we studied a ravine and the width of a rock. And so we're just applying it to some real world context here. And here we're trying to find the distance across a lake. So if you would, go ahead and go to the bottom of the page and draw a line. We're going to chunk items 1 through 4. So with that in mind, go ahead and work items 1 through 4 and then play through the video. Okay, hopefully you took a moment to actually explore items 1 through 4 before playing through the video. I do want to point out that this diagram is very, very similar, and the diagrams we're going to look at for the rest of this lesson are very similar to the Try These A, Part A on page 264. So what we're learning here, we're going to explore what's called the triangle proportionality theorem, is actually going to help make it a little easier to find this distance, dA, which is actually just a portion of a complete side of a triangle. Hopefully you can observe that dA is not a complete side of a triangle. It's only a portion of side CA. So we're going to actually find how this theorem helps us find the distance from D to A a lot quicker. So the first thing we had to know was, in this example, very similar to our national park example, is we had to know that the two triangles were similar. Remember in lesson 18.2, we first have to know if the triangles are similar in order to use proportions to solve for missing sides. So they tell us that MR, that line, is parallel to ST. Well, anytime we introduce parallel lines into a diagram, we have to wonder, are they trying to tell us that corresponding angles are congruent, alternate interior angles are congruent, same side interior angles are supplementary? Any of those we learned with our parallel lines might come into play. So I wrote angle, angle, or side, angle, side. Those are the two we explore in 18-2. So if these two lines or line segment are parallel, then angle AMR, you see here, is congruent to angle AST because those are corresponding angles of parallel lines and they have to be congruent. Is that ringing a bell? Corresponding angles congruent? Isn't that how we've been describing similar triangles? That their corresponding angles are congruent? So we see this terminology come back over and over again. Also, angle A, and I'll actually mark it in the diagram, angle A is congruent to itself because of the reflexive property. Now, why will we even bother mentioning angle A? Well, angle A is a part of both triangle AMR and triangle AST. So we have two pairs. Technically, that's a pair because it's involved in both triangles. That pair and this pair are congruent. Therefore, the two triangles are similar by angle-angle similarity. Well, I love what they said in number 2. Knowing that the corresponding sides of similar triangles are proportional, complete this proportion. So we figured out, or we showed that the 2 triangles were similar. Now we can write a proportion. So I actually finished out the proportion. AM, which is this complete side. I know you can consider AM a portion of AS, but it is a complete side of this much smaller triangle. AM corresponds to AS, and AR corresponds to AT. So they give us some different samples of information and ask us to solve for it. So notice I kind of redrew the diagram here and kind of replaced it with values. So we know that this distance, A to M, is 12, and M to S is 9. So to find AS, I did 12 plus 9. That math we saw back in lesson 18 too. So this side of the smaller triangle, AM, which is 12, corresponds to this side of the larger triangle, which is 12 plus 9, which I show is 21 here. And likewise, on this other side, we said that AR, which they told us is 15, corresponds to AT, which would actually be 15 plus X, just like we did 12 plus 9 to find AS. And so that's what's represented here. Then we perform cross multiplication. I'll tell you that before I multiplied 15 times 12 and 9, I went ahead and added 12 and 9 together. So I got 21 times 15 equal to 12 times 15 plus X. I'll tell you it'll work out the same way if you multiply 15 times 12, 15 times 9, then add that together. That's literally what you're doing right here. So I multiplied 21 times 15 and got 315, and distributed 12 times each of these terms and got 180 plus 12x. I knew I had some like terms, 180 and 315, so I subtracted 180 to combine to 315 and got 135. In order to get x by itself, I divide 12x by 12 and 135 by 12, and I found that the missing measure of RT was 11.25 centimeters. You might have done it a little bit different, and I'll tell you, more than likely, and I'll actually show you, if you wrote this proportion, 12 over 9 equal to 15 over x, you were actually using the theorem in this lesson before you even knew it was possible to do that. Because think about what you did. You compared a whole side, because that's what 12 technically is, it's a whole side of this smaller triangle. You compared it to a part of the larger triangle. Think 9 is just a part of this larger triangle. So you compared whole to part, but you did the same thing on the other side of the equal sign. You compared 15, a whole side of the smaller triangle. You compared it to a corresponding part on the larger. And that's how these ratios work, or these proportions work. As long as this ratio is similarly written to this one, you can solve in a very similar way. So if you do 12 times x and 15 times 9, you'll actually see you get 135 equals 12x. So you kind of bypass all of this work to still find the same conclusion. The trick here was you didn't actually know that this would work, or it wasn't proven to you that this could work, because this is actually a new theorem. So with that in mind, look at the work for item 4. You can follow the path of the work that I did here. Same thing. This distance, which is a whole side of this smaller triangle, I said that x corresponds to x plus 8, this whole side of the larger. So x corresponds to x plus 8. Likewise, I did 25. That corresponds to 25 plus 10, which of course we would know would eventually become 35. Cross multiplied. This became 35, so I multiplied 35 times x. And I multiplied 25 times x plus 8. Doing that distributive property, I get 25x plus 200 equal to 35x. I combine my like terms, 25x and 35x, by subtracting 25, because it's positive. To move it across the equal sign, I have to subtract. And then I divide both sides by 10 to find that AM is 20. But let me show you probably the math that you did, and again, you didn't even know was possible. Potentially, you took the distance here, which is a whole part of this smaller triangle, and you said it corresponded to 8, which is actually just a part of the larger triangle. And then you set that equal to 25, which is, again, a whole side of the smaller triangle. And you said it corresponded with 10, which is just a part of the larger triangle. Any idea what you get when you multiply 25 times 8? You get 200. And when you multiply x times 10, you get 10x. So we can actually arrive at this measure a lot quicker by using what's known as the triangle proportionality theorem. So let's figure out why this works in this instance and to know when we can use this concept to use this work that can make it a lot quicker. So let's actually look at the definition on the next page of triangle proportionality theorem. So it says if a line parallel, remember we saw that in the initial diagram, if a line parallel to a side of a triangle intersects the other two sides, then it divides them proportionally. So what we're seeing here, and we have this example, we're not actually going to work through this proof, but what we're seeing here is if this line is parallel to a side of a triangle, in this case PE, and it intersects the two other sides, IP and IE, then it divides this larger triangle proportionally. So that this section of the larger triangle actually can correspond to this section. Look here, B to A. B and A correspond. And likewise, C corresponds to D. So we're going to use that, if you want to call it a shortcut, because the triangle proportionality theorem exists, we're going to use that to help us solve these problems a lot quicker. But remember, the key here is if a line is parallel. So we have to know it's parallel first before we can use the shortcut. So we're actually going to go and move on to item 6. So if you would, draw a line right above 7, pause the video, use what you have learned. You can use what we did in 18.2 or use the theorem here to find the distance of the lake from D to A. Okay, so now that we have seen the triangle proportionality theorem, you can use the theorem to solve the problem from the beginning of the lesson. So notice I showed you the method from lesson 18-2, and then I showed you the method using the triangle proportionality theorem. Obviously, one is shorter than the other, and this should be our go-to. Remember, the only reason we can use the theorem is if these two sides are parallel to each other. That's very important here, because if this side or this line is parallel to a side of a triangle, then this line divides this larger triangle proportionally. So here's the work from 18.2, and here's the work from the theorem from this lesson. And notice at a certain point, we arrive at the same equation. It just took us a little bit longer to get there using the method we learned possibly in 18.2. But regardless, the length of DA is 56.9 kilometers. Because ED is parallel to BA, CE corresponds to EB. And CD corresponds to DA. So that's the work that was done over here. So CE being 27.5 corresponded to EB 54, and CD, which was 29, corresponded to our missing measure DA, which is X. And we found again the distance 56.9 kilometers. Now, if you would, go ahead and draw a line above number 8, and just take a moment and write the converse of the triangle proportionality theorem. So swap, the hypothesis and conclusion of the definition on the previous page. Okay, so here we've taken the opportunity to write the converse of the triangle proportionality theorem, and I probably wrote it just a little bit differently than you. So it says if a line divides two sides of a triangle proportionally, then it is parallel to the third side. Remember, it said if, for example, if FE was parallel to YZ, then it divided the triangle proportionally, such that A corresponded to B and C corresponded to D. So now we put that in reverse and say if A over B is equal to C over D, which is a proportion, if this proportion is true, then line FE has to be parallel to YZ. That's the converse of the proportionality theorem. So now we're going to forge ahead. Always take a moment, work to check your understanding. We don't always do that together on the videos, but it's excellent practice here, especially applying what we just learned. We're actually going to forge ahead to item 11 using the triangle proportionality theorem in conjunction with what's known as the parallel proportionality theorem. So obviously you probably look at this diagram and your mind starts to go crazy, but think about what it is. It's really just one large triangle that's divided by these lines proportionally. And the reason I know that is that they say that RE is parallel to AT, which is parallel to IO, which is parallel to NS. So all four of these segments are parallel to each other. In other words, they are dividing this much larger triangle proportionally. And that's what the parallel proportionality theorem tells us. If two or more lines parallel to a side of a triangle intersect the other two sides of the triangle, then they divide them proportionally. We're just adding more lines to our problem. So if you would, pause the video, work item 11. So I will draw a line at the bottom of the page before playing through the video. Okay, so if you actually took the time to try to figure out the length of each of these missing segments, you probably ran into potentially some difficulties here. So let me try to explain through that with all the work that you see here. So before I go any further, I want to explain what these three proportions mean. It is very important, and we keep saying this word over and over again, proportion. It's very important when writing a proportion that there is a link between your ratios. So notice on the first proportion, I can compare a whole side of a triangle to a part of a triangle. But in the other ratio, I have to also compare a whole part of a triangle and, in fact, of the same triangle and compare it to a part. So notice the link. So we can compare whole to part, absolutely, but on the second ratio, we have to compare whole to part. Well, likewise, another way to approach it is instead of dealing with parts at all, we can look at it as whole sides of triangles. So we really need to be able to understand what is a whole side of a triangle, a complete side, if you will. So another way we could write our proportions is compare a whole side to a whole side, and of the other ratio, a whole side to another whole side. And we'll see some examples here in our work. And the last point to make is we can compare a part to a part and set that equal to a part to a part. So that is very important in our study of proportions and the link between each of these ratios. So without further ado, let's take a look. So ET, first thing I want to point out, ET is a part of a triangle, not a whole side. ET is a part of a triangle. So notice what I compared it to. You could either view CE as technically a whole side of triangle CRE, or you can compare it to a part of triangle CAT. And this is where the triangle proportionality theorem comes into play. Because we said if RE is parallel to AT, then RE divides CA and CT proportionally, such that ET corresponds to CE, just like RA corresponds to CR. So that's what I did here. Now be careful when writing your proportion. Notice I chose ET and compared it to CE, So in my other ratio, I have to go to a similar side or a similar part of the other side. I apologize for that. So we did ET compared to CE, and on the other side, we chose a corresponding side or a corresponding part to ET, RA, to correspond to CR. Using cross multiplication, we found 32 centimeters, and so I added that to the diagram. I do want to stress, and a lot of you have been noticing, this is not the only proportion we could write, or even the only way we could solve these proportions. This is just one method to do it. So let's look at item B. AI, again, a part, not a whole side, but it's a part of triangle CIO. So I compared AI to TO, a very similar part of triangle CIO. So if I compared AI to TO, a part to a part, then I compared it to a similar part, CR, look, AI, CR, from TO to CE. Used cross multiplication and found AI was 30 centimeters. And as you solve for these different segments, be sure to add those distances to your diagram. Now, C is where it gets a little bit tricky. Notice I put a little star by C. I also put a star by E and F. This is where it gets a little bit tricky. Up until this point, we've really been comparing parts to parts. But the problem is on item C is we are tasked to find the distance from A to T, which if you look at AT is not a part of any triangle. It's a whole side of triangle CAT. So we're going to now utilize whole to whole. So AT will correspond to RE. I believe that's what I did here. So these are corresponding parts of two different triangles. So now, to use for the second ratio, I need to find another whole side of the triangle that AT is on. So I believe I chose correct CA. So AT corresponds to CA. A whole side, AT, corresponds to CA, another whole side of triangle CAT. Well, to find the distance from C to A, I simply added these two distances here and got 60 centimeters. Well, what corresponds to RE the same way that AT corresponds to CA? Well, RE corresponds to CR. So I said RE corresponds to CR the same way AT corresponds to CA. I believe some of you might have actually gotten 20 centimeters doing it a slightly different method, and make sure that your measurements make sense. Look at the diagram. The distance from A to T is clearly greater than the distance from R to E. Think about it this way. Imagine triangle CRE is dilated using C as the center, and these new triangles are created by dilation, an enlargement dilation. So the distance from A to T definitely had to be greater than the distance from R to E. Now, we look at OS, which now we're going back to a part, correct? OS is simply a portion or a part of this larger triangle, CNS. So I compared OS, this portion, to a similar part on the other side of the triangle, IN. So OS corresponded to IN, and in a similar fashion, pun intended, I use CE. Notice it's another part on this side of triangle CNS. I use CE corresponding to CR. Again, we're looking at the larger triangle CNS. I cross-multiplied, found that X is 16, therefore OS is 16 centimeters. So now I actually have the length of every single segment on these two sides of triangle CNS. So I now need to find IO and NS. And IO is the tricky one here again, because IO is not a part or a portion of a triangle. It's actually a complete side of triangle CIO. So when we perform this proportion, we need to compare IO to another whole side in a similar triangle. So IO, I believe, and I'll check just to make sure, I compared it to something we already found, AT. So IO corresponded to AT. Well, then in the second ratio, I had to choose another side that's on the same triangle that IO is on. So I chose another whole side, CI. Well, then I had to figure out what corresponded to CI, but was also a whole side of the same triangle that AT is on. And I chose CA. So IO corresponds to AT and CI corresponds to CA. Used cross multiplication and found 67.5 centimeters. Last but not least, potentially the one that gave us trouble as well. Again, the reason some of this stuff really causes issues for students is because comparing parts, comparing similar parts. NS, again, is a whole side of a triangle. More specifically, triangle CNS. So I need to compare that to a whole side of a similar triangle. Well, fun fact, all of these triangles are similar. So I compared NS, I imagine, to IO because it's close. So if I compared NS to IO, now I need to go back to the triangle that NS is on and pick a whole side of that triangle. I imagine I chose CN, but let me just make sure I did. So I did NS, compared it to IO, and then chose CN, so I need to compare that to CI. Notice the similarity here. CI corresponds to CN. They're on the same side of the triangle. And CI is a whole side of the triangle that IO is on. So once I create that proportion, cross multiply, and solve, I find my last segment of the triangle, 76.5 centimeters. So take some time here, especially those that might have caused you some issues. And I know this diagram looks a little bit intense, but it's all about writing proper proportions. I believe if we can do that, we'll be successful here. Now, the last thing we're going to look at is actually the converse of this theorem. So the theorem tells us if two or more lines parallel to a side of a triangle intersect the other two sides of the triangle, then they divide them proportionally. So the converse of this would be if two or more lines intersect the other two sides of the triangle and divide them proportionally, then the lines are parallel. So that's what we're trying to figure out here. Notice what A has asked us to do. It says if Grant Street and Newton Street are parallel, what's the value of X? And then B, we're tasked to determine are the streets parallel. So we're going to use the converse here. So if you would, draw a line under part B. We're going to chunk these two together, and feel free to use the My Notes section. I probably will. And make sure you support your answer on item B before playing through the video. Okay, hopefully you took some time before playing through the video. But let me explain what's going on here and why it's super important how we found our answer to item A. So it says if Grant Street and Newton Street are parallel, what's the value of X? So we are not going to claim that Smith Street is necessarily parallel to Grant or Newton. And why is that important? So we almost need to ignore Smith Street right now and the division between these two segments here. I'll tell you why. Because if these two segments are parallel, then it divided this triangle, this larger triangle, proportionally right here at Grant Street, not also at Smith Street. So I went ahead and found the distance between these two streets here, or these 2 points. And I found it to be 830 feet. And same thing, I found the total distance here, 770 feet. That's super important because we can only use the parallel proportionality theorem or even the triangle proportionality theorem if these segments are parallel. And again, the only ones in question are these two. So the way I wrote my proportion was I compared x, a part or a portion of this larger triangle, to a similar part on the other side of the triangle, 520. And again, if you start with this side of the triangle on the first ratio, you have to start with this side again on the second ratio. That's why I chose 770, this distance here. Again, we have to ignore Smith's street because we have no idea if it's parallel to Grant or Newton. And 770, this side, corresponds to 830, just like x corresponded to 520. And notice I changed the equal sign to an approximate sign because we got a decimal in 482.4. Then part B then asks the question, and again, A, we assumed they were parallel, found x. Now we want to know, are the streets parallel? And to do that, we use the converse of the theorem. So if Smith Street divides this triangle, let me highlight it in green. If Smith Street divides this triangle proportionally, then Smith is parallel to Grant. So we're ignoring these measures down here, not even taking into consideration 520 and x. So how do we know if it divides it proportionally? Well, we compare corresponding sides. So I compared 320 to 450. I actually compared two parts on the same side of the triangle, which is acceptable, or you could have done 320 over 350. Well, if I did 320 over 450, then I had to go to the other side of the triangle and compare 350 to 480. Well, if you notice, here is that proportion. When I cross multiply, I get two very different values, which tells me that this ratio is not equal to this one. Well, let me explain what this math is over here. One way to write a ratio is a fraction. Well, another way to write a fraction is a decimal. So I wanted to also show you that you could change this ratio to a decimal and then compare the two decimals. And so we see here that 320 over 450 as a decimal is 0.711 roughly, and 350 over 480 is roughly 0.729. So two ways to show that these ratios are not equal. And if these ratios are not equal, then corresponding sides are not proportional. And if corresponding sides are not proportional, Smith Street is not parallel to Grant Street. Well, that is the end of lesson 18-3, which means it's the end of activity 18. So as always, go back to your learning targets, reevaluate them. And if we're still not hitting 5s on our learning target, watch the video again. Watch the parts that might confuse us. As always, check out the lesson practice, as it is an excellent way to get better at this work. And thank y'all for watching.